This is T210 computer system. Which of the following is the logical expression that indicates the output X of the combinational circuit below? Here, the dot is used for the logical product. The plus is used for the logical sum. And the bar above any letter or number represents the negation of that. Here we have our four answers and the combinational circuit below that's described in the question, and let's see which of these is the correct answer to our question. In digital electronics, a NAND gate, or a negative AND, is a logical gate which produces an output which is false only if all its inputs are true. Thus, its output is complement to that of the AND gate, hence the negative AND in the sentence, the negative AND gate. The NAND gate is significant because any Boolean function can be implemented by a combination of NAND gates. This property is called functional completeness. The NAND gate is one of the two universal gates, with the other being the NOR gate. A NAND gate, being a universal gate, can be used to implement a NOT gate. Here we have the circuit which has been used in the question circuit of combinational logic we had on previous slides. Let's analyse this and see what our output is. If A is 0, both inputs to the AND are 0. So A and A will always equal 0, whereas A and A knotted will always equal 1. So there what we've done is we've inverted A to be A is equal to not A. However, if our inputs are both 1, so A is equal to 1, A and A is equal to 1, so A and A knotted is equal to 0. So again we've managed to invert our input to become the inversion. The truth table shows that the consecutive AND and NOT operation in one input produces the resulting of a NOT gate. This can be used to analyse our circuit on the previous slide. Using the knowledge we gained on the previous slide, we can redraw our circuit to be a simplified form, with our inputs A and B, then go into a simple inverter rather than the complicated AND NAND gate that we had on the previous slide. These then go into another NAND gate here, and our output is X. So we're trying to see what implementation of the NAND gates that we had in our actual Boolean algebra. So here our X is equal to not A and not B, all knotted. What we can do is we can use De Morgan's theorem on this operator here, and we can produce the following outcome. This is equal to A inverted twice, ORed with B inverted twice, which is simply equal to A or B. So let's compare this to the answers that we were given in the question. Here we have the logical circuit that gave us our output of X is equal to not A and not B, all inverted. We used De Morgan's theorem on the previous slide and derived the outcome to be X is equal to A or B. So B is our correct answer by comparing this to the original question slide. So here we can see our answer is B. And what we've learnt in this video is how to use De Morgan's theorem to analyse our NAND equivalent circuits as to what they would have been originally in Boolean algebra.